Yeah.
Hi everyone, thanks for joining us for the February 2025 2DCC webinar. The speaker today is Dr. Ravichandran from the University of Southern California. And Dr. Ravichandran, you are good to go ahead and begin. Thank you.
Thank you so much. Can everyone hear me well?
Yep, we can.
Okay, perfect. Thanks a lot for inviting me to give this webinar today. It's a pleasure for me to present in front of the folks at Penn State 2DCC Center. Um, what I'm going to talk about today is on thin film growth of highly vapor pressure mismatched materials. Um, there are a few words that are pretty uh, bombastic here, but the whole idea is if when you're trying to grow materials and if you have multiple components, and if those components tend to have completely mismatched vapor pressures with large differences, there are significant challenges in growing those materials in high enough quality. And this is an issue that I'll try to go over why this is important, how this also sort of ties to some of the thematic interests for the 2DCC Center itself broadly. Um, so let me get started with a few important slides. The first one is the acknowledgements. A lot of the things that I'm going to show today was done in close collaboration with several wonderful colleagues, not only at USC, also at other places all over the world. Specifically, and I'm grateful for the collaborations with Rohan Mishra at WashU and Yutsun Shao, who's a new assistant professor in our department. Both of them doing a lot of microscopy work. Rohan also does a lot of theory work related to stuff that we have been interested in. Some of the early collaborations with Megumi Kawasaki on compaction of chalcogenide materials, Han Hatun and Huan Zhao, who's now at ORNL on some of the spectroscopy work. Special acknowledgements to Bharat Jalan from Minnesota, who, even though is not a collaborator in these works, but has been a very important sage advisor for the technique developments that I'm going to show here. A lot of the work here, the most of the work that I'll show here is done by Maithili Surendran. She's moved on to a postdoc at LBL now, and several others in my team, including Shanwan, who's the early student who started a lot of the chalcogenide work that is done in my group in the last 10 years or so. It's a couple of things about the funding. Major funding came from Army Research Office, and then we have also have some supporting funding from NSF and few other, including ONR on the crystal growth, not necessarily directly related to that, but broadly in the chalcogenide area. So this is an overview of my group's research in general. So just a quick flash. My group studies a lot of novel materials for electronics and photonics with a strong focus on chalcogenides, specifically sulfides. We have worked on a lot of these materials that have strong light emission in the visible energies. We've done some work on how do you process these novel materials, particularly perovskite structured chalcogenides, in terms of some sort of photo detection device structure. And also we have studied the fundamental optical anisotropy in these materials, which is of interest for a lot of the polarization optics that we want to develop for mid and long wave infrared energies. We also have a healthy amount of work on phase change materials in terms of some of these chalcogenides that we have been growing also have some interesting phase change properties. The other aspect that I'm very invested in and very passionate about is the development of novel synthesis and characterization techniques, particularly characterization techniques that are in situ and also often fairly advanced ones and synchrotrons that we can leverage to understand these materials at a deeper level. The other quick plug I want to give is for the Center of Excellence in Nanoimaging, which is a center that I co-direct at USC. This is housed in one of the relatively newer buildings at USC, Michelson Hall for Convergent Biosciences. This characterization center is right next to the clean room, and it has three important thrusts on advanced electron microscopy. So we have a relatively new now. I mean, it's a couple of years old now, Spectra 200, where we can do aberration-corrected STEM imaging. We also have a suite of cryo-electron microscopes to study biotic matter, and also a variety of X-ray probes, including a small angle X-ray scattering beamline or mini beamline. And some of the results I show here comes from Shah's group, where he has used our Spectra 200 to get some of these nice results that he had done, similar to what he had done in Professor David Muller's group at Cornell in the past. For more savvy people who can use QR codes and so on and so forth, you can use this barcode to check out our website. So why do we care about thin film growth of electronic materials? I mean, sort of preaching to the choir here. Penn State has a long history of studying electronic materials of various forms over the years, and some of these aspects should be very apparent. I show some examples. The first one on the left is basically a TEM image of FinFET, where you can clearly see you have a surround gate oxide to the silicon channel that is embedded inside, and you get this nanosheet type structure that is being developed recently. This involves an interesting silicon germanium silicon heterostructure growth and then processing to get the sudden gate structure. You also are seeing some of these light emission devices where you're creating quantum cascade lasers and so on and so forth by leveraging the ability to grow 3/5 and atomically precise structures with well-defined compositions. On the right, something that should be extremely familiar to several in the audience, particularly, I think I saw Professor Chen had logged into the talk on the oxide heterostructures, where development of some of these polarization textures has been of interest in the oxide community in the last decade or so. Um, so how do these influence our life? I mean, there is this fundamental aspect of can you see novel phenomenon? On the other aspect of applied interest, lots of these energy technologies are becoming much more solid state oriented. Solar cells, some of these photoelectrochemistry systems people are talking about, and also thermoelectrics invariably would need some sort of solid state involvement, and this more and more start to involve thin film growth, particularly if you're thinking about miniaturized devices. On the other hand, quantum computing and neuromorphic computing and other next generation computing technologies people are talking about involves advanced materials, often beyond silicon materials, which require, again, thin film growth. And last is the communication and sensing area, where there's a lot of interest in leveraging some of these atmospheric windows in the infrared, particularly in the mid and long wave infrared. And they follow very similar patterns of trying to grow these detectors and other photonic devices in thin film form. So the new electronic materials with new functionalities, particularly their processing methods, are of great interest to continue to advance these technologies. I'm going to try to dial down and try to focus on some of the chemistries that I'm going to try to relate to in this particular talk. The type of materials that I'm going to talk about are chalcogenide materials. Again, very intimately tied to the themes of what's pursued in the 2DCC Center. There's a whole slew of layered materials, which are typically transition metal chalcogenides. There's also tetrahedrally bonded main group chalcogenides, something like zinc selenide, zinc sulfide, cadmium selenide, cadmium selenide, and sulfide, and so on and so forth. There is a large number of tetrahedrally coordinated complex chalcogenides, including SIGs and CZTS, and so on and so forth. Last but not the least, the most recent entrant to this list of chalcogenides is the chalcogenide perovskites and related phases, where you have this ternary alkaline earth metal like barium, transition metals such as zirconium and hafnium and titanium, and the sulfur or selenium on the X side, which forms these octahedrally coordinated structures. So there is a lot of chemical variety, structural variety in these classes. But one thing that you may start to notice is that there are significant challenges even with main group systems in the growth of these materials, and it gets much more perverse when you think about materials that involve transition metals. Why does that happen? The idea is the mismatch in the vapor pressure in these materials. So this is a plot of the vapor pressure of various elements that are of interest to us here. As you can pay attention to it, something like sulfur, tellurium, and even selenium, for example, tend to have very, very high vapor pressures, even at very modest temperatures. Whereas the other materials, such as titanium and other transition metals that we routinely see here, tend to have very, very low vapor pressure, even at fairly high temperatures. To give you an idea, if you compare a select group of these elements that I showed in the previous slide, even at 500 degrees Celsius, you can see that the difference in the vapor pressure are dramatic, which means how do you ensure that you can control the flux of each of these species in a reasonable manner. At room temperature, it gets much, much worse, which means um, invariably you may have to evaporate or produce some of these vapors of the low vapor pressure materials and some other techniques to do some level of matching of the vapor pressures to get your growth to work well. Um, so some issues when you're trying to grow these materials using conventional vapor phase high vacuum type techniques is the precursor for sulfur an important choice one has to make, and how do you want to go about it? The most simple choice of precursor here would be elemental sulfur or molecular sulfur, if you want to think about it that way, and it has extremely high vapor pressure. But as you change the temperature of the temperature at which you are trying to crack your sulfur, the relative ratios of various different types of molecules that you can get changes dramatically. And this also tries to push your sulfur equilibrium back and forth depending on what sort of conditions you're working with. And this leads to very poor incorporation of sulfur. The controllability is fairly bad. And on top of it, invariably, some of the common sulfur sources, which are a little more reactive, can be implemented a little bit more, tend to be much more toxic, corrosive, and leads to lots of issues in having a very reliable growth process. One example is hydrogen sulfide, which is always considered a little more reactive than the elemental or molecular sulfur, but puts a lot of stress on the type of vacuum equipment and the monitoring that you do with, like, for pressures and so on and so forth. So this leads to this very important challenge. When you have mismatched vapor pressure, you invariably have to grow these materials at high temperature, which is not favorable for your chalcogen, but at the same time for your transition metal or other refractory species that are present in your compound would require higher temperature for increased surface mobility. This also leads to some uncontrolled reactivity issues of what these species interacting with your substrate or within the material itself. Do they form uncontrolled structure or composition as you keep growing these materials? This leads to poor structural and compositional quality, and also interfacial roughening and intermixing and so on and so forth. So now what I want to do is to sort of take back and go a little bit more into the details of the specific categories of materials that I'm going to talk about, and then we'll come back to some of the growth advances so that we can go hand in hand in how we do think about these things. So as I mentioned in a couple of slides ago, the motivation to sort of solve this problem from my point of view came from the interest in this ABX3 type perovskite chalcogenides. For example, if you take this ABX3, the prototypical material you can think of in the chalcogenide side is the barium, zirconium, and sulfur, where barium goes into your A site, zirconium goes into your B site, and sulfur goes into your X site on your faces. And this leads to a BX3, BX6 octahedra. And depending on what sort of composition you have, it will decide how your whole structure evolves here. And of course, this perovskite structure comes from the calcium titanate, which is the prototypical material based on which perovskite structure was discovered. And if you take this framework and you start thinking about changing your A, B, and X elements, the nature of how you connect all these octahedra together changes dramatically. For example, for if you have your ABX3, closely follow the Goldschmidt tolerance factor, then you can have this corner shared perovskite-like structure, either cubic or distorted perovskites, or you can force the system to have edge sharing, where instead of the corners, you're now connected through the edges, and that leads to a little bit lower dimensional systems. And you also have this quasi 1D phase shared systems where you can have this 1D, highly anisotropic 1D chains running along the C-axis, and there is a hexagonal tiling on the AB plane. And lastly, you can take the same ABX3 structure and you can start to interleave rock salt layers, which is this AX layers, and you can start to get lower dimensional layered structures such as Rudolph poppers, and then Dion Jacobson faces, and so on and so forth. So this gives us a lot of variety of materials to work with, and besides trying to think about how do you grow and process these materials, we were also sort of interested in some level of materials design to pick some materials and try to investigate very specific properties that could be of interest here. The first case is this quasi 1D hexagonal systems, which are this phase shared materials, and they have a couple of interesting behavior that we have seen so far. One is that they tend to have extremely large optical anisotropy. What do I mean by that is that the refractive indices, either the real or imaginary part, tend to be extremely different along the chain and across the chain. And this leads to large birefringence, large dichroic windows. Then you can think of using these materials for filters, or using them for wave plates and other polarizing optics that allows you to shape the wavefront of your uh, uh, light. And specifically, they seem to work extremely well in the some part of the mid IR, and also large portion of your long wave IR, which is of interest for this atmospheric window communication and sensing that I mentioned earlier. The other interesting part is, turns out some of these materials are on the verge of some sort of instability. And we have shown that BATIS3 undergoes a couple of interesting electronic phase transitions. And this is work that we are continuing to investigate. It won't be part of today's talk, but just showing that there's a lot of interesting physics and even phenomenological applications that one can think of. The other type of interest is in this distorted perovskite type compositions. And the big motivator for this class of materials was this spectacular rise in the power conversion efficiency of the halide perovskites, which prompted people to think, if you're going to have something special about this perovskite structure, where halides tend to have a lot of stability issues, perhaps chalcogenide perovskite could act as a more stable version of it, but still you can get some interesting optical properties for photovoltaics or other applications. So this is early work that was done by Shenbai Zhang's group at RPI, where he was able to predict some of the basic properties of these chalcogenide perovskite and highlighted potentially BAZRS3 as an interesting solar cell material. That led the community to go look into these materials a little bit deeper. We spent a lot of time trying to grow some of these materials. We've shown that these materials can luminous over a fairly broad energy range that ties nicely with the solar optimal single junction energies. We also showed that they seem to have fairly interesting attractive optoelectronic properties, very good thermal stability. You can heat them to say 500 C or so, and they still don't oxidize completely or degrade. So they are fairly good for operation at high temperatures. And also there's some work where people show that they seem to have much higher absorption coefficient, which also opens up the possibility of ultra-thin photodetectors or even solar cells of these materials. So there was a lot of after the lot of interest in the bulk properties of these materials, there's a lot of work that started emerging in the thin film growth. There were two-step processes that were developed where you deposit the zirconium oxides and then you try to sulfurize them in a high temperature sulfurization system using CS2 or other sulfurizing agents. There's a lot of improvements that allowed people to grow fairly crystalline materials down to 500 or even 400 degrees Celsius. There was some work on the solution processing of these materials, which lowered the processing temperature significantly. There's also work on sputtering and then rapid thermal processing to get these structures. Invariably, all of these techniques involve two-step processes, sometimes high temperatures, and not always fairly large grained or even high crystalline quality materials with these approaches. So one of the early questions that we had is, can you grow direct single step thin films of this chalcogenide perovskites? So this is why we built the first generation hydrogen sulfide compatible PLD system at UC. This was the early Those works was started around like 2018 or so, and my student Maitli, who worked on closely designing and building this system in the beginning, and once we had set up some of these systems with relatively corrosion resistant parts to ensure that these systems don't break down all the time, because typical PLD systems that you buy are much more compatible with oxides, but not necessarily corrosive systems such as sulfides. Our first challenge was to get nice, dense polycrystalline targets for the thin film growth itself. There were a few different approaches that we tried. We tried to do the high temperature hot pressing technique, which was not super successful, presumably because it's done in the reducing environment, which leads to some side reactions, non-stoichiometry after we process it. So we talked to Professor Megumi Kawasaki at Oregon State, where she was using this high pressure torsion technique to study fine grained metals to see if they can do the same thing for the sulfides, and turns out was reasonably successful, which allowed us to get first generation 90% dense targets. Then my group, we acquired a cold isostatic press. This is almost close to 800 megapascal hydrostatic pressure, which allows us to center targets not as great as the HPT, but close enough to this number, which allows us to get a lot more targets at this stage for most of the sulfides that we are interested in. So the first experiment, the successful one that Maitli was able to achieve, was when she started growing these materials at various temperatures. She was playing around with the background gas pressure. We were limited to less than 5% of H2S diluted in argon for safety concerns. But presumably these dilute concentration was sufficient to grow reasonably textured films, as you can see here, where yeah, I'm showing the thin film growths of BaZrS3 on a couple of different substrate, lanthanum aluminate, strontium lanthanum aluminate, and each of these cases we get this 101 textured films. When you do reflectivity, X-ray reflectivity, you get reasonably smooth films. Um, um, you may want to remember that the substrates are not necessarily the ideally lattice matched or chemically very compatible system. But we were pretty happy that we were able to achieve this back in 2021. And this was a concurrent demonstration of the chalcogenide, like BaZrS3 thin film growth with Professor Rafael Jaramillo's group at MIT, and they had used MBE to grow these materials. We studied the epitaxial relationship in these films a little bit more carefully. And if we do the pole figure mapping of these films, you can clearly see there is a one-to-one matching between the in-plane relationship, your substrate and your film. And we were able to map out this relationship completely to show that you have a very unusual interfacing between the film and the substrate, where we would have nominally expected the film to rotate 45-degree to minimize the lattice mismatch. But in these cases, it seems like you produce a large number of interface dislocations to just grow them without any rotation at all. We also noticed that there's significant interfacial damage in these cases, presumably because of argon or even the hydrogen sulfide reacting very aggressively with the oxide substrate underneath. So while we could get a reasonable idea of what the lattice matching and the epitaxial relationships are, the interfacial quality was not that impressive as we would like to be. So we also studied its optical properties. Turns out we could measure very reliably the absorption coefficient once we started growing them in thin film form. It was much harder to do in crystals, or nearly impossible given what the geometry of the crystals we were getting at. And we also saw luminescence very similar. It was very muted and very similar to what we saw in our single crystals, presumably something intrinsic to BaZRS3, which is something we have studied on other occasions. We also compared the energy at which your luminescence happens compared to the absorption edge, and they seem to match reasonably well with the literature within the error bar of the energy ranges that people have reported. We also studied its optoelectronic properties in using time-resolved PL. The numbers were really similar to what we got for our single crystal, suggesting that overall quality, even though it tends to be polycrystalline, the overall quality is comparable to what you would get in the high-quality bulk materials. So this is work that was done in collaboration with Juan Zhao and Han Hatun at Las Alamos National Lab. Juan has moved on to Oak Ridge now for his current position. We also made the very first generation photoconductive light sensor, basically, of these materials. The early versions, we spent a little bit of time trying to work on minimizing the dark current in these materials while processing. We also had some work suggesting that polishing these materials would lead to a lot of deformation twinning and other extended defects. So once we were able to figure that out, we showed that we can get fairly good on-off ratios. There is still sufficient amount of defects. That's why you do see photoconductive effects here. But nevertheless, this behavior is significantly better than what other people have managed to report and similar in other thin film materials of this BaZRS3 composition. Um, so we came to a point where we realized there's significant challenges still in the growth of these materials, and we wanted to sort of take a step back and think about developing some novel techniques where we can really address how we can grow high quality thin films of these materials better. Our interfaces are still not as great. As you grow at fairly high temperatures to crystallize these materials, the multi-layer stacks we would grow are not abrupt at all. But if you grow the same stacks at 400C, you can see that you can get fairly good abrupt interfaces, but crystallization was challenged. So there was a catch 22 here where we tried to heat up increase the temperature to get crystallization, but then the interface abruptness goes away in this case. So we thought we'll take a step back and try to see what other techniques one could use to solve this issue. And this is when we started talking to Professor Bharat Jalan at Minnesota, who had developed a lot of these hybrid MBE type techniques. And we started trying to incorporate the sulfur precursor using a metal organic or a organosulfur precursor instead of our argon H2S to try to see if that resolves some of the issues that we are seeing here. And we designed a very simple zero generation precursor inlet system. And this is work again, Maithili published a year ago, where we were able to create this hybrid PLD technique where our pressures in the chamber are not as high as what you would have with argon H2S. It's mostly flooded by this precursor, and then you can do the growth as usual that you would do for a PLD system. Now, there are some design considerations for this. What sort of precursor do you choose and why? And we went through this whole list of precursors, and we identified the uh, sulfur bonded terbutyl disulfide as a good choice because you do get fairly appreciable vapor pressure at modest temperatures like 100 degrees Celsius. And presumably, the if you have a single sulfur connecting alkyl chains, the cleanliness in which they cleave and try to interact with your material seems to be significantly better once you go to the terbutyl disulfide. And that's why it's also widely used as an ALD or MOCVD precursor for chalcogenides. So we learned about this beta hydrogen elimination mechanism, which makes this much more conducive to get cleaner, nicer growth of these materials. So we chose this as our precursor material and we started trying to do some growth. In this case, we started taking a step back and try to think about, can we grow a variety of different chalcogenides? So we said we're going to give it a shot with our the chalcogenide perovskite. We have been interested in BAZRS3, BATS3, but we'll also start looking at some of the binary simpler chalcogenides, such as the alkaline earth chalcogenides like barium sulfide, strontium sulfide, calcium sulfide, main group chalcogenides such as zinc sulfide, and transition metal chalcogenides such as titanium sulfide and zirconium sulfide. And I shows a select few where we do get textured growth. I'm showing barium sulfide, which represents the alkaline earth metals, and the main group zinc sulfide and the transition metal titanium sulfide. In all these cases, you can grow at relatively benign temperatures. You don't have to go as high as 700 C, and you can still get nice reflectivity, thickness oscillations in extra reflectivity and texture. So this made us pretty confident that something is getting better with this technique. When we started looking at the rocking curve, what we noticed was in general, the rocking curves are pretty narrow below, say, 500 degrees Celsius, but you go to higher and higher temperature, it seems like there's a lot of island formation and then roughening, which leads to much poor coherency in your rocking curve itself. But overall, it seemed like the rocking curve itself is reasonably narrow, given that these are highly heteropitaxial thin films that we are growing on pretty much incompatible substrates because there are now commercially available high quality substrates for many of these materials. So what's the epitaxial relationship between barium sulfide? The choice of substrate we picked here was strontium titanate. It's a perovskite, rock salt and perovskite, but turns out you still have some reasonable epitaxial relationship. You can see that the interface is much nicer compared to what we saw in barium zirconium sulfide. And we do get a very good epitaxial relationship between our substrate and your film, all the way from calcium sulfide to barium sulfide, with barium sulfide seems to have the highest quality. And presumably, even in the stability sense, barium sulfide is much more stable than the other alkaline chalcogenide materials. So we collaborated with Hsieh, where he did all this STEM imaging and also EDS to check the composition. They seem fairly uniformly distributed. And we looked at the growth of zinc sulfide. Zinc sulfide is a material that many people have grown many along using a variety of techniques over the years. In our case, we could get a reasonably high quality zinc sulfide even down to 300 degrees Celsius, fairly sharp interfaces when you grow at 400 degrees Celsius. Is a representative a Bragg reflection where you can also see these Pendesilong oscillations and also Kisik fringes in your reflectivity. Um, we had some challenges in doing a standard reciprocal space mapping using our thin film diffraction system. So we used our small angle X-ray scattering, where it was a much easier way to get all these reciprocal space map, and we could get a little bit better sense of what sort of in-plane epitaxial relationships we have. And when you combine with STEM imaging and looking at the in-plane relationship, we were able to map out the exact in-plane relationship in these cases. So even though you're trying to grow a tetrahedrally coordinated chalcogenide on STO, turns out you can get fairly good epitaxial relationship and reasonably high quality materials in this case when you're trying to grow these binary materials. The last one in the binary category is this titanium disulfide. We were able to grow fairly textured materials. Their in-plane coherent domains are not necessarily as large as what you would see in some of the CVD techniques people use, where they get these large triangles, but we are trying to grow them uniformly everywhere, and we don't really limit our flux control as much as what you would do in the case of CVD in the high pressure turbulent regime. But nevertheless, we can get fairly textured films, good metallicity with a very large RRR, comparable to single crystal values in the literature, suggesting that the films of this quality are fairly good. Then we went back to solve some of the issues that are related to the growth of the chalcogenide perovskite, which motivated a lot of our work here. And even in this case, after we resorted to the hybrid PLD technique, the texture was not significantly better than what we started with in the case of our argon H2S. But nevertheless, we wanted to go back and check what are there anything intrinsic to the materials itself that limits our growth, or is it related to how well our processing conditions and so on and so forth work. What we noticed is this interface smoothness does get better when you compare the argon H2S technique compared to the hybrid PLD. And when you use hybrid PLD, it seems to be a lot more benign in the reaction with the interface of your substrate compared to the argon H2S, where presumably the argon that is ionized tend to really attack the substrate and the film and make it much more polycrystalline. But the amount of improvement that we were expecting was not observed, so it probably says something about something fundamental about these ternary systems, because as I showed earlier, we can grow barium sulfide thin films fairly good epitaxial quality. We can also grow titanium sulfide thin films fairly good epitaxial quality. But when you combine both of these, it seems the growth of the ternary system seems to be much more challenging. So this vapor pressure mismatch still seems like an issue that we'll have to work on. We have some new ideas that we are coming up with to try to solve this issue. So then we took the hybrid PLD, barium zirconium sulfide, and the argon H2S PLD, barium zirconium sulfide films to compare the optoelectronic properties. One thing that really stood out is that the dark current that we get in our hybrid PLD systems are significantly lower, a couple of orders of magnitude. That suggests that the point defect control, or in general, the defect control is much better in these materials. We also did other routine characterizations such as Raman spectroscopy, PL, and so on and so forth. PL seems to be the not so sensitive probe here, primarily because of something very intrinsic to BAZRS3 here. But nevertheless, I think our optoelectronic measurements seem to have a much better handle on trying to probe its quality than even PL or other pure light-based optoelectronic studies. Okay, so with that, I want to show a brief, quick demonstration of our ability to grow chalcogenide bilayers and superlattices. Since there is still challenges in the ternary system, we resorted to growing these structures using the binary systems such as zinc sulfide and titanium sulfide. You can see that you can get fairly smooth bilayer structures. The superlattice reflections do show up. It's not as impressive as the oxide systems that we can get in MBE or PLD currently, but this is just the first step towards trying to take some of these materials and try to show that we can get some heterostructures or bilayers or even superlattices out of these materials. I think we still have a long way to go. We still have to have better substrates, better control of the surface mobility, reactivity of these materials. And we have some ideas to try to resolve some of these issues, but perhaps it'll take a little more work before we can really solve these issues. Um, so one of the things that we are starting to think about is our ability to try and use some photo-assisted techniques to control the surface mobility and also even precursor decomposition and so on and so forth. There's a lot of work, ton of work in the 2.6 and also 3.5 systems where people have used these approaches in the past. It might benefit us a lot more given that the vapor pressure mismatch between transition metal and chalcogen is way more dramatic compared to even the main group ones that I show here. And they did see in many of these cases significant improvement in the structural, optical, and optoelectronic quality of the films that they were growing. So we think that this is an area that we might invest in the next some time to try to get a better understanding of what are the mechanistic aspects that one needs to address to bridge this vapor pressure mismatch gap to get better quality films of this kind. So to conclude, I hope that I have shown that chalcogenide perovskites are an interesting class of electronic materials which pretty much prompted our interest in trying to develop some of the growth techniques I've shown here. We were able to develop this new hybrid PLD technique, which is sort of similar to some of the other approaches that people are thinking about in the oxides. I know Professor Changbom Yum's group at Wisconsin has been working on some of the hybrid type techniques to address some of the stoichiometries on the cationic side. This one is on the anionic side. We've grown epitaxial barium zirconium sulfide using argon H2S and also now using hybrid PLD technique. There are still some open questions, some mechanistic questions about how these things work. We have used read to a limited extent to learn a little bit about it, but I think more in situ characterization is needed. In an unrelated work, my group has developed or improved on some of these existing in situ OJ electron spectroscopy techniques for oxide thin films. We anticipate that could help, and maybe adding a little bit more in situ characterization will allow us to gain better insight into how to grow these materials better. Lastly, I think the fabrication of devices, particularly photodetectors or other geometries, would allow not only for practical applications, but also to probe the quality of the materials that we are preparing using these techniques, because sometimes structural and chemical analysis that we do has its own limitations. And beyond a certain point, some of these electronic and opto-electronic probes can be much more valuable feedback for giving an idea of how to improve these materials. I hope I didn't go too fast. That I would like to conclude, and if there are any questions, I'm happy to answer.
Thank you so much. Does anyone online or in the room have any questions? Okay, it doesn't look like there are any questions, so thank you again.
Thank you.